Let's begin with our problem. A garden hose held near the ground shoots water at an undetermined speed. At what angle should the nozzle point in order to extinguish a fire that is 4 meters away? So here we have our fire at ground level, and our hose will also be at ground level. But since the water is coming from the hose's nozzle, we'll set our origin to be there. So our question is asking, at what angle should the hose's nozzle point in order to extinguish a fire that is 4 meters away? We began our approach to solving this problem by finding the time and then the velocity of our hose. We held the hose 1 meter from the ground, but since our origin is at the nozzle, our measurement in the y direction is negative 1.0. When we sprayed the hose, the water traveled a distance of 6.6 meters in the x direction. With this data, we can calculate the time and velocity using a derivative of our kinematics equation.
We concluded the change in the x direction is 6.6 meters and that the change in the y direction is 1.0 meters. And the formula that we derived for time is t equals the square root of 2y over negative g. So if we just throw in those numbers, see, 2 times 1.0 over negative 9.80, t equals the square root of 0.20, and that comes out to about t equals 0.45 seconds. Now that we have the time, we can find the velocity. The formula that we derive for velocity is initial velocity equals the change in the x direction over time. Put theta if you want, doesn't really matter. So v initial is 6.6 meters over 0.45 seconds. That comes out to 14.6, but because of significant figures, we round that to 15 meters per second. That's our velocity. Now we have to find the angles at which we can hit this fire. Okay, so the formula that we derived for range is range equals initial velocity squared sine of 2 theta over g. Or if we don't know the angle, which in this case, sine of 2 theta equals r g over initial velocity squared. Now, we measured the fire to be 4 meters and velocity 4 meters from the starting point, and the velocity to be 15 meters per second. So let's plug in those numbers now. Sine of 2 theta equals 4.0 meters times negative 9.80 meters per second squared over 15 meters per second squared. And we just do the math. Sine 2 theta equals negative 39.2 meters squared per second squared, right? Yeah, it would. Over 15 squared, 225 meters squared, second squared. So all that stuff cancels out. We're left with the sine of 2 theta equals negative 0.174. And we just take the inverse sine of that. So the arc sine of that, just going to remove the negative. It doesn't matter if you keep the negative here or not. I'm just going to move it to make it less confusing later. So that is 2 theta, some lead, equals 10 degrees. But since it's 2 theta, it's between 0 degrees and 180 degrees. So it's 2 theta equals 180. Sorry about that. 2 theta equals 180 degrees minus 10.0 degrees equals 170. But divide that by 2. So theta equals 85 degrees. And to find the second angle, we just take 90 minus 85, which is 5 degrees. And these are the two angles at which you can hit a fire that's 4 meters away with a garden hose that has the velocity of 15 meters per second.
At this angle, the water shot directly into the fire. Let's observe if it has the same effect at 85 degrees. When we held the nozzle at 85 degrees, the water was falling like rain within the vicinity of the bucket.